In the previous lesson, we have been emphasizing on the first ionization energy. This meant that we are removing an electron away from a neutrally charged atom. However, there are times where we intend to remove more than one electron from the atom. For example, in the case of magnesium, we know how the first ionization energy compares to form a monovalent Mg+ ion. However, we are also interested in the second ionization energy to form the more stable Mg2+ ion, and why Mg3+ ions hardly exist as we study its third ionization energy. Essentially, the ionization energy increases as we seek to remove more electrons. Consider this. After the first ionization, there will be less repulsion among the remaining electrons in that shell. However, the nuclear charge of the atom remains the same. This meant that each of the valence electrons now experiences a greater effective nuclear charge and requires more energy to overcome this attraction force. Removing an electron from an already positively charged ion requires much more energy. Hence, we can see that the first ionization energy is usually lesser than the second, which in turn is lesser than the third, and the trend goes on. At the point where all the valence electrons of an atom has been removed, we will then observe a great jump in ionization energy. For example, for magnesium, the first ionization energy is 738 kilojoules per mole, the second ionization energy is 1450, but the third ionization energy jumped to 7730 kilojoules per mole. This is because in the case of magnesium, after removing the 2 electrons from the n=3 shell, the third ionization energy involves the removal of electrons from the inner core, and in this case it is the n=2 shell. Because this third electron we are attempting to remove is of a lower energy level that is closer to the nucleus and therefore more strongly held by the nucleus, the amount of energy is definitely going to be much greater than the first 2 ionization energy. This sharp increase is applicable to all atoms and it appears directly after all the valence electrons have been removed. For example, the second IE of sodium is significantly higher than the first IE, while for aluminium the first 3 IEs are lower compared to its fourth IE. Based on this, we can also predict what is the most stable form of cation and that the metals will form.